All right. Now, a lot of what I'm going to talk about here to begin with this parametric equations with trigonometry stuff, is kind of outlined on the beginning, or on the front part of your worksheet you guys are going to look at today. So, I still want you to write this stuff down, but it is right here too. But there are some identities that you guys have looked at in the past that we're going to utilize here today. And these are ones we looked at in Chapter 5. Okay, and they're these Pythagorean identities. What they're going to help us do is create equations that come from parametric equations that had some sort of trigonometry involved with them at the beginning. Okay, so like for example, if you had, let's say, x of t equals cosine of t and y of t equals sine of t, then what is that one equation that puts those two together? If you guys remember back in the A section of this, when we did parametric equations, that was kind of our goal, was to take the two x and y equations, eliminate t somehow, and then put those together. Okay? And our process for doing that before was, well, you take one of the two equations, solve it for t, and plug it in the other one. Now, that's problematic with trigonometry because if we try to take one of these two and solve it for t, then we end up with an inverse cosine or an inverse sine, right? And then we'd have to take that and plug it back in. Well, we want this to work for every single t that we could possibly plug in. If we do that, if we go that old route and try to solve one of the two of them for t, all of a sudden we have an inverse cosine or sine. An inverse cosine and sine, if you guys remember, had those restricted domains. They don't work all the time. There's only certain parts of the unit circle that you can use for them, right? Okay? And that's problematic for this because we don't want it to be restricted. We want everything. So we kind of have to take a backdoor approach to it a little bit. We can't go directly the way we did before. Okay? And we're going to use some of these identities to do it. And it's still going to involve substitutions, but it's going to be substitutions that are a little different from what you're used to. Okay? So first thing we're going to do here is I'm going to use the identity that's going to be helpful with this one. And that's this. You guys remember that one? Cosine squared t plus sine squared t equals 1. Nope, it's not even that complicated. I'm going to rewrite these things so it'll make the substitutions just a little bit easier. I'm going to take them out of their function notation, but ultimately this is the same exact thing, right? X equals cosine of t, and y equals sine of t. Like I said before, we're used to trying to solve one of them for t and then plugging that into something, okay? But if I rewrite this one, too, in such a way, I think that'll make it a little bit more obvious. We're going to do a substitution, but it's not going to be quite the same.
So we're just going to stick that in there.
If x is equal to cosine, you can not only replace x with cosine, but you can replace cosine with x. And down here, since y is equal to sine, you can not only replace y with a sine, but you can also replace sine with a y. So think about this. If I'm going to do a substitution into here, okay, I'm going to take this cosine t, make it an x. Take this sine t, make it a y. So what do we ultimately have there then? X squared plus y squared equals 1. Remember, the goal is to take these two equations and eliminate t and have an equation that only involves x and y once we're done. Did I do that? Yeah, in kind of a weird way, but I did. I got rid of t. Okay? I took a known identity and made a substitution into it to do it. Okay, I found an identity that involved cosine and sine, because that's what I had to work with here. And I was able to do it, and I got this. Does anybody remember what is this an equation of? It's a circle. So if you have the parametric equations cosine t and sine t for x and y, it actually makes a circle. That's what the graph of that thing looks like. Okay?
Trying to figure out how to graph a circle in the parametric mode.
That's how you do it. Cosine and sine. Yep. All right. Let's try another one. I'm going to use a different identity with you here. Another identity that we looked at was tangent squared t plus 1 equals secant squared t. It's another one of your Pythagorean identities that we had. So let's say I want to take x of t equals 2 tangent t and y of t equals 3 secant t. I'm going to do kind of sort of the same thing here. Okay? Now over here, again, you don't have to rewrite it this way if you don't want to. I think it just makes it easier though. We've got tangent t squared plus 1 equals secant t squared. That's really what that is. If I try and do the same type of thing that I did with the last one, it's not exactly going to work out right now, right? I can't just turn this into an x and turn this into a y. Why not? We got some coefficients that are kind of screwing the deal right now, right? It's 2 tangent. It's 3 secant. So what should I do before I can make those substitutions there? Divide them. Yeah, divide the 2 to the other side. Divide the 3 to the other side.
1/2 x squared plus 20.
Yeah, you got the right idea. Yep. So x over 2 equals tangent, and y over 3 equals the secant. But as soon as you've done that, you're ready to roll again. And now we're plugging in these fractions instead of just x and y by themselves. Okay? So again, I'm going to take them, dump them in. So instead of tangent, I'm going to make it an x over 2 squared plus 1 equals, my secant is y over 3 squared. Okay, so that's kind of it in its raw form. I've just made those substitutions. I've eliminated t again. I'm good to go that way. The only thing I'm going to ask you guys to do from here is to just simplify that up a little bit. Okay, and in this case, what I mean by that is eliminate all fractions that are in there. Okay, so we can do that. It's just going to take a little bit of multiplying through by some constants, and we can do it. So if I actually multiply these out, though, because I got to square them, this is actually x squared over 4 plus 1 equals y squared over 9. So I've got a 4 and a 9 in my denominators there that I want to get rid of. What could I multiply the entire equation by to eliminate all of those fractions all at the same time? 36. Yeah. Okay, because 36, 9 and 4 are both factors of 36, so we know that's going to take care of both of them. Okay, so see if we can do this in our head. If I take the 36 and I multiply it by x squared over 4, what's that going to leave me with then? Except get rid of the 4. Right? Because the 36 would have canceled that out. So yeah, it would have left the 9, 9x squared. What about the 1? That's just a 36 now. Yep. And then what about the y squared over 9? 4y squared. Yep. So that would be what I'm looking for with this one then, completely simplified, eliminating the fractions in the process. Okay? Don't need to solve it for y. Don't have to do that much. But just leave it like that. Okay? So this right here, this is not one that you probably recognize. Okay? We are going to talk about these at the end of chapter 8. We'll get to these. This is a hyperbola. And maybe you guys, I don't know if Algebra 2, did you guys get into doing that? Nope, it's hyperbola. Anyway, so you guys, Did you guys in Algebra 2, did you get to like doing ellipses and hyperbolas and parabola, none of that kind of stuff? They're called conic sections? No? Good. Okay. That's fine. That's fine.
That was the trimester of too many snow days. So.
That part got cut out then. Anywho. Yeah. There's a major axis and a minor axis, and yeah. We'll talk more about that later. Anyway. What you've just made here, though, is a hyperbola. It's going to look like a hyperbola, which we'll talk, like I said, more about later. But, all right, let's try one more. And then I'm going to show you how you can graph these things on your calculator and take a look at them. And then that's basically what you're going to be doing in your homework, is doing this and then sketching a graph of what it should look like on the calculator. Okay? So, all right, the other identity that we haven't used yet is cotangent squared t plus 1 equals cosecant squared t. So this one, I'll try and come up with one here that will work with those then. And just so you guys are aware, too, on your assignment, I'm not going to tell you which identity you have to use. That's going to be part of what you need to do, is to figure out which one's going to be useful. But I wanted to show all three of them here, so this one's going to use this one. Except I'm going to get a little sneaky. Okay, so let's say I got x equals tangent t and y equals 4 cosecant t. What's the problem? Yeah, there's a tangent instead of a cotangent. Why the heck would I do that to you? Yeah, exactly. You can just take the reciprocal and you're good to go. So, I don't have a cotangent to use. However, I have something that I could rewrite as a cotangent, and so then I'm fine. So, I'm going to take these two equations here. I'm going to make x 1 over cotangent t, because then I got it in terms of something I can use. And then my y, well, I'll just leave that as 4 cosecant t for now. Okay, so each one of these, top one I need to solve for cotangent, the bottom one I need to solve for cosecant. Then I have something to substitute. Okay, so if x equals 1 over cotangent, then the cotangent of t equals what? 1 over x. Right. And then the other one you can do just like you've done. Cosecant of t would equal y over 4. And then go plug them in. Okay. So cotangent squared in this case would be 1 over x squared plus 1 equals y over 4 squared. And then it's going to be that same kind of song and dance where you got to multiply them out, simplify it so there are no fractions, that sort of thing. So we've got 1 over x squared plus 1 equals y squared over 16. So again, what can I multiply the entire thing by to eliminate all the fractions? Yes, 16x squared. All right, so if we were to distribute that in, then let's see what happens. 16x squared times 1 over x squared. That's just a 16, right? The x squareds cancel. 16x squared times 1. 16x squared. 16x squared times y squared over 16.
Y squared, x squared.
Yep. And I'm going to just make it x squared, y squared, because usually you go alphabetically, just convention. But that's it. That'll work. All right. This guy is not a hyperbola. This one, I don't know if it has a name, actually. I don't remember. It looks kind of strange. We'll maybe graph this one to do the example here. But there are certain ones like the last one where I just recognized what the formula looks like from doing lots of them in the past. This one's not recognizable, at least not to me. Anywho, if you want to look at it, you got to make sure that your calculator is in parametric mode first of all. Okay, so go to mode, and then where it says func, par, pol, and seq, you go to par. Now, in this case, with these guys, we're not doing vectors anymore, right? Back to radians then. So make sure you're also switching your mode back to radians. And then if you go into your y equals menu, you should see something like this. Okay, so if there's anything that's still typed in there, clear all that out of there. And then also double check that these plots are all not highlighted either. If they are, just go up to it, hit enter, and then go back down, and it'll take care of it. You don't want your plots turned on at the same time if you can stand it. All right, so those equations that we made, the ones involving x and y that eliminated t, we're not typing those in, right? We're typing in the original parametric equations that we had. Okay, so in this case, it was the x equals tangent and the y equals 4 cosecant. So x equals tangent, that's easy. We can just make it tangent. 4 cosecant, we can't type that in directly, right? There's no cosecant button. But what is a cosecant? It's 1 over sine. So I have 4 times 1 over sine. Let's do it like that. Or, technically, 4 over sine would work too. But 4 cosecant t. Okay. Remember with parametrics, we're really interested in our window too, to make sure that we are seeing everything. Keep in mind we're in radians, so your t min and your t max. I'm going to make you go negative 2 pi to 2 pi, just so we've got kind of a wide area to look at. The t-step, this was the how often do you want it to plot another point. If the t-step is really small, it's going to be a nice smooth curve, but it's going to take a long time to graph. If the t-step is large, then it's going to graph it really quick, but it's going to be kind of jagged looking. So I always go like 0.01 on that. Sometimes it makes it go kind of slow, but it should be okay. And then the x min and max, y min and max, all of that stuff. Just want to make it pretty large. That you might have to go back and change if it looks really small or doesn't look like it's catching all of it. I'm going to just keep it negative 10 to 10 on each of those for right now. The scale doesn't really matter. We'll keep them at 1. But that at least gives you kind of a standard window to start with, and then you can kind of modify it as needed depending on what you see. But if we hit graph, see if we can get a look at this thing yet. Yeah, maybe so. Alright, that should be all of it, right?
So we're going to have to graph each one on our calculator then?
Yeah, and you're going to just make a little sketch of what you see. Oh, come on. It'll take that much time.
2 minutes to graph this thing.
Oh, well, you'll survive. Okay, so this one has that kind of a look to it. Now, remember, parametric equations, when we graph them, they're not always functions, right? Is this particular one a function? No, definitely doesn't pass the vertical line test. In fact, the very first one we did was a circle, right? And circles don't pass the vertical line test, so that wasn't a function either. Sometimes they are with these. Sometimes they are, but most of the time they're not. But this equation right here has this graph then associated with it. Okay? In parametric mode, it would be this, but in regular Cartesian equation mode, it looks like this. It's called a Cartesian equation if it has x and y in it. Yeah. New vocab for you. You don't need to know it. I'm not going to quiz you on it or anything, but Cartesian equation, that's what it is, x and y. So in any event, that's what the graph of that thing looks like. So using this type of stuff to create a Cartesian equation, using the calculator to graph what it looks like, that's all I need you to be able to do for this stuff. Okay? So, all right, let's give it a try.